So now the third part, this is also warm-up training. If you look at this equation, you will not, probably not at once, be able to decide whether this equation has any solution at all, and if it does, how many solutions would we expect? And so it's important to find all solutions. And it actually, it can easily happen if you don't take care that you quickly find a solution and then you just overlook the other one. So first of all, what's the definition set of this equation? That's a good idea to make this clear first, so that in the end we know what we have to expect as a solution. And now I say that the definition set should be R plus. You know what I mean? I think Martin uses the notation greater or equal 0. This is the short notation for positive real numbers. Why? Okay, I tell you. I don't allow x to be 0. That's easy because this would be a division by 0. So that's clear. But why doesn't x why must x be positive? Why is it forbidden to be negative for x? Now that's actually because of the logarithms. You know what LG means? It's a short notation for here. You see, LGx is sometimes used for the logarithm base 10 of x. So that's the so-called decadic. Yeah, I think it's called the decadic logarithm base 10. Now, anyway, all the logarithms are exclusively defined for positive arguments. So here and also here, x must be greater than 0. So in the end, this would be enough, because if x is greater than 0, it can't be 0. So the division by 0 wouldn't happen anyway. So that's it about the definition set. Yeah. Now, there is a definition set. I should have said the range. Okay, so it's just no range. Sorry, how's it called? Just missing the word. What's the official? When I say definition set, this D set.
Domain.
Right, I'm sorry, domain, that's what I mean. So in German, it's called Definitionsmenge, Definitionsbereich, and of course, we have been calling it domain all the time. So sorry, I was talking about the domain, okay? So now, if you have a little practice about logarithms, you will immediately see that this 5 to the power of negative LGX is easily transformed into the reciprocal of 5 to the power of positive LGX. You know that? So it's like, it's sometimes called the law of negative logarithm. Well, you could say like this. Log, don't care about the base, any logarithm of any base of a divided by b. This is the second law of logarithms, can be written as a difference, you know that? And then as a special case of this rule, we find that the log of 1 by b, for example, then would be log of 1 minus log of b. And here you see why it is that, because the log of 1 is equal to 0 always, for any base, so it doesn't matter which base you use. It means that the logarithm of the reciprocal is equal to minus the logarithm, yeah, of any value. And you can also put the minus sign here. So if you get something like this, well, is that what we have? Actually, it's not. I'm talking about the wrong thing here. I'm sorry. It's really connected, but that's not what we need. Let me put it away. You may help me. I was talking about the law of negative exponents, of course. And I was willing to inform you that, of course, a to the power of minus b equals, yes, reciprocal of a power b. That's all I wanted to say. Okay, so we can take this one and say this is the same as, so this one is the same as 1 by 5 to the power of LGX. And that's what I did first in my head. And then I combined these two expressions as to be x power LGX divided by 5 power LGX. And then I pulled the LGX outside of this fraction. That's what I was doing. Okay, I guess you've already recognized. So why do I do this? Well, if I look here, it's very striking that 25 is the square of 5 and x squared is the square of x. So there's a similarity between both sides. And so in the end, I have x by 5. This quantity to the power of LGX should be equal. And now, to put this in a slightly different form, 5 divided by x, this quantity squared. I just put the squaring outside. And now I see that this is the reciprocal of this one. So it's easy to change this again by the same law as before, by taking the reciprocal x by 5 and then changing the sign of the exponent. So now I have something I can easily compare. I have x fifth power LGX equals x fifth power minus 2. So now there are two possibilities for this equation to be true, to hold. One possibility is to say the exponents should be the same. Since this exponent is dependent on x, of course, it means that if I choose it if I choose the exponents to be equal, this has an influence on the basis value, but the basis value is the same anyway on both sides. So actually it's allowed just to demand that LGX equals minus 2, negative 2. So we have the same exponent and also the same base then. This regardless of which value x takes. So then LGX should be equal to minus 2. I can just remove the logarithm by taking 10 to the power of left side, right side. I get this cancels, 10 to the power of LGX, 10 to power of LG cancels and x stays there. So x should be equal to 10 to the power of minus 2, which is of course nothing else than 100. Okay, so that's the number we get as a solution, and we can test it. Yeah, if you just test, let's do it. Test it here, putting it putting in for x. So we have 100 power LG of 100. But the LG of 100, of course, it's like the LG of, of 0.01. And, it's like counting the zeros or the movements of the comma, 1, 2. So this is, of course, negative 2, as everybody knows. Okay, so I have, like here, I have 100 to the power of negative 2, and then times 5 to the power of minus the same number. So the negative of this one is then 2. And this is, in the end, it's 1. Well, if you will, I can pull this up. So this is also the same as 100 power 2. So like 10,000. 10,000 times 25, so it's 250,000 in the end, left side. The right side is 25 divided by 100 squared. This again is 1 divided by 10,000. So I can also pull this upward and say this is 25 times 10,000, which is equal to 250,000, just for a little test. Okay, but the second solution is not, it's not to be overlooked. And well, the reason for the second solution is quite subtle. I tell you, the reason is that the exponent is quite arbitrary as long as the base equals 1. You know that potentiating 1 is has no effect. And that's why the exponents may well be different for this equation to be true if the base equals 1. It's quite simple. It's like saying x by 5 should be equal to 1. In other words, x equals 5. You can test it also, and this one is even nicer. If I set x equal to 5 here, I have 5 to the power of LG5, but times 5 power minus LG5. So this is this time it's an expression which neutralizes itself. You may know I can then put it has to be 5 power LG5 and then divided by 5 power LG5 if I use this law of negative exponents again. And so this, of course, equals 1. And the right-hand side, of course, is 25 divided by 5 squared. So 25 by 25 equals 1. So that's it. Okay. Like I said, another warm-up. And then we can proceed shortly to the real sequence and series exercises.